All right, welcome everybody. We're going to start in a minute or so here. I just want to make a couple of preliminary announcements before we get going. First, on behalf of myself and my co-convener, Doug Drager, we want to thank AGU for encouraging us to organize this late-breaking session and providing rooms and times that were not Monday morning or Friday afternoon. There's going to be three sessions associated with this special session on the North Korean September 3rd, 2017 declared nuclear test. There's a set of 8 talks now from 4 to 6 p.m. here. Tomorrow morning, there'll be a set of 8 talks as well. It'll be in a different room. It'll be in room 225 to 227. And then tomorrow afternoon, there'll be a poster session with 23 posters downstairs in the seismology area. So I want to thank everybody that contributed. We got 39 abstracts to this late-breaking session, so a very good international turnout and interdisciplinary turnout. So it should be a very interesting session. So our first talk this afternoon is Detected Surface Effects of the September 3rd, 2017 Declared Nuclear Test by Frank Pabian. And Frank will be giving the talk.
Well, thanks, Bill and Doug, and appreciate you coming out and for this opportunity to give this talk. I'm going to just focus on what we can observe visually as well as the implications from what can be observed non-visually from INSAR, and I'll leave that as a lead-in segue to the following talk. I only have a few textual slides, but basically Mount Mantap at Punggye-ri Nuclear... What? So what? Can you hear me? I got to get closer. Okay, sorry. Okay, the Punggye-ri nuclear test site has been the location of 6 acknowledged underground nuclear tests, and this presentation provides a review of the observed widespread surface disturbances generated by the 6th test, the largest to date and estimated to be close to a quarter megaton, with magnitude of about 6.1. Some people say USGS published 6.3. You'll hear more about that following up. And we do a visual comparison of pre- and post-test commercial electro-optical satellite imagery, and the surface disturbances that were observed include multiple small landslides, primarily on the southern slope of Mount Mantap, cracking, subsidence slippage, spall, rock falls, and even tree falls. And I'll show you where we can actually show trees that were up before the event and knocked down after the event. And these visually observed surface disturbances correlate well with those that were detected based on synthetic aperture radar, interferometric synthetic aperture radar, INSAR, analysis as done by other researchers. And there's also a short official video. When I say short, it's about 1 second, that was found on the internet by other researchers, published by the Dprk, that actually recorded the, or apparently recorded the event in progress. And you can see a dust cloud rising and what looks like a rock fall in progress. And the most significant surface disturbances were noted in the 200 meters, the upper 200 meters of volcanic deposits layer above the more well-indurated, solid basement rock, the diorite granite below. And if you want, there's references there, but you can just Google it online, 38 North. When you look at the comparison, it's published by the CTBTO of the signals, and you compare to what we observed before with surface disturbances. The first event in 2006, there were no detectable surface disturbances. Same thing in 2009, and same thing in 2013. But then in 2016, January, the first event that year, there were some barely detectable surface disturbances, and I'll show what we saw from that as comparison with what we see on the most recent. Also, there were a little bit more detected in September 2016 event, and then as you can see, the signal is much bigger by comparison. There's widespread surface disturbances with the most recent event. This is kind of a generalized map layout conjectured based on what we know about where the events occurred using relative relocation and mapping and anchoring the Dprk-4 event, the January 2016 event, in the upper left-hand corner of Mount Mantap. And when you do that, it looks like this is pretty much where they lay out. There can be some argument about this, and I'm willing, all I can say is it's conjectured, but it looks pretty good based on some things that we know. For one thing, the North Koreans published. If you look at this area here, this is a plan diagram that was published in an animation video by North Korea. It was a propaganda video, but there's a lot of interesting features in that diagram that correlate well with how other nations have designed self-concealing, self-containment mechanisms for self-sealing mechanisms using a fishhook that were used by the French in Algeria and the United States in its first event. If you go to Plum Bob Rainier nuclear test, the tunnel layout, there's a lot of similarities there between the North Korean diagram and what was actually done, including the blast debris traps, the tunnel bends, and the fishhook at the end. Also, also the interior. This is the interior of the Plum Bob Tunnel, 1957, and the interior of the Pakistani test tunnel in 1998. A lot of similarities. It's basically, it's more crude in the Pakistani, but it still did the job. And we can imagine it's pretty much the same with North Korea. When you look at the cross-section, you can see where the tunnel portal is on the left, the lower left over here. Let me see if I get this going. Down here. And as shown in the cross-section, at about 1405 meters elevation, all the way up to 2205 at the top. And so you have an effective depth of burial and the effective overburden together is about 800 meters, as opposed to what was the Dprk 5 event in September 2016 and going back to the one in 2009, based on where they occurred on the surface, and you just go down and subtract the tunnel entrance elevation, you get those depths. As far as anchoring, I talked about how we had a pretty good empirically derived anchor for the test in the fourth test, the Dprk-4, in the upper left-hand corner of Mount Mantap as you're looking at north up. And so we feel pretty good about where that one was located, and that's from Matt Way. And then here's the surface disturbances that were detected at the time. In 2016, you can see a before and after. The problem is that we had a large temporal window from mid-December 2016 to 6 January 2016, which just happened to be only 40 minutes after the event. And it looks like on fresh snow, we could actually see a boulder come down, and it looks like some of the snow was popped off, you know, from spall. So we can't prove it because of the temporal window is so broad. We had also in September 2016, we saw some small landslides. This is what it looked like before the test in September 2016. This is what it looked like after. So you get an idea of the differences. I'll go before, after, pre-test, post-test, okay? And there's the nonconformity between the stratified volcanics. This is about 200 meters in elevation between the nonconformity and the basalt cap, where there's an escarpment up there, and then the basement diorite granite below. This is looking down on the peak, and the geolocations as mapped by NORSAR is the large ellipse there, pretty much centers on Mount Mantap where the maximum elevation is located. Wen's group in China plotted the event here. In the whole scheme of things, it doesn't really matter. They got the mountain right, but I think we're going to use this as our basis for this discussion, and we'll see why. But it doesn't. We can't prove it either way. We just, based on everything we know, it's somewhere in the mountain. And then this is what it looked like pre-test, vertical view of Mount Mantap with an existing scree field up here. And there was a landslide scar from the 2016, September 2016 event, the fifth test here. Again, you can see that where the stratified volcanics are located, there's lots of scree fields and landslides, pre-existing scars. This is what it looked like post-test. So I'll go back and forth. This is pre-test, pre-test, post-test. And it may not be real obvious, but there is discernible differences. And we'll talk more about that in a minute. Then this is an overview, September 1st, so this is 3 days or 2 days before the event, and we have 1 day after the event. So this is pre-test, post-test, you ignore the clouds, pre-test, post-test, and then we'll zoom in. This is pre-test, post-test, pre-test, post-test. And I'm going to move it a little bit faster here. Pre-test, post-test. Then just to show you where some of the INSAR data pointed to the greatest amounts of subsidence, et cetera. This is some INSAR work that you'll hear about a little bit later. And it plotted most of the activity occurred in that upper left-hand corner where the slope is steepest. I'm going to go a little bit faster. Same thing here. The whole mountain moved. And then there was this INSAR that was published by Monterey Institute, pre-test, post-test. You can barely see it, but most of the activity that's detectable on these two images, that pair of images, is in the stratified volcanics area. Moving right along, this is a close-up of that area where we saw trees get knocked down, the pre-existing slide scar. That's post-test. So pre-test, post-test. Also in the lower part down here, there's cracking. And if you watch, you go pre-test, post-test, the crack shows up. Then here's a close-up where there's two standing trees that are identified there. And then post-test, they're knocked down and towards each other. One fell north upslope, one fell down south slope. And or fell south downslope. Same thing, another image a little bit later, all the trees were defoliated because of the time of year, but even on the ground you could see that the trees are still in place, so we correctly identified those as down trees. Here's a close-up of those two standing trees with that pre-existing slide scar from the 2016 test. There they are down, so they're up and they're down, and then they're down again in the next image. And then there's this area where we had a rock outcrop. There you can see the shadow. And another, this image was taken in 2015, but it was taken November 2nd. The reason I used it is because of the shadowing. So it's almost the same time of year as the next image. So the shadows and the time of day were the same. So this is post-test. So this is October 30th. Pre-test is on November 2nd. So if you look at the shadows, everything points in the same direction, same amount of shadow, but you can see that the main outcrop, the shadow disappears. You can also see there's a 60 meter by 6 meter crack crevice with apparent cracks in the upper right. I mean, not upper right, but the upper left right there. So this is huge compared to what we saw before. There's pre-test, post-test. This is that video at freeze frame with the dust cloud rising. This is how it compares to a Google Earth generated visualization. For comparison, the features that you see here are matchable on the Google Earth and where the geology is located, and then there it is as a composite. So we can actually see that bright spot as a rock slide. It occurs right where there's an existing slide area, and it was probably a rock falling and caught in the process. So finally, the September 3rd North Korean underground nuclear test was geolocated in the Mount Mantap Peak. It was likely the most deeply buried, we're saying about 800 meters, and had the largest magnitude. There was widespread surface disturbances were observed on publicly available commercial satellite imagery subsequent to the event. There's close correlation between those surface disturbances as visually observed with those with INSAR data and SAR data. Their subsidence compression was noted primarily in the top 200 meters of Mount Mantap, which is the volcanics layer. There were two localized zones of slippage subsidence that were observed in the southwestern or if you, left side, let's say the left-hand corner of the mountain. And given that the likely depth of the test device was placed at about 800 meters below the peak in granitic rock, it's highly unlikely that these subsidences represent any surface expressions or cave-in of a cave-in or collapse of the underlying cavity. And one last thing, I only got like 30 seconds, but I want you to be aware of this. Laeslo Zerbo published this on a tweet saying, here's the most recent tremors since, well, all the tremors since the 3rd September event. And I happen to overlay a geologic mosaic published by Ron Matsko from the USGS. And then when you zoom in and you make it a little bit transparent, you can see where they plot. And then when you zoom in, you can see those three over on the right. They actually plot right here on this map that we have published, and it's they overlay areas of known faulting in the Meisen-Kilju Graben. And if you're interested in seeing the geologic maps, we have this published by the defense agency U.S. Defense Department has published this, and I'll give you the links. And then here's a cross-section diagram just to show the Graben, and that's it. Any questions? Is that it? Are we going to wait till the end, or?
No, we have time for a question. For Frank?
Anybody? Okay. Not, you can meet me after. Oh, you have?
I was wondering about the sense of motion on those faults. Is it clear that it's, I mean, is there information that's entirely dipslip? Is there any evidence of?
That's what the cross-section looked like. I don't know if we can go back. Yeah, it's hard to say what it is from just what we have, but you take a look. We have the original data. Oh, and by the way, those geologic maps were from Japan from 1925, and they're still good. Geology doesn't change. Okay. All right. Thanks a lot.
Thank you, Frank. So our next speaker is going to be, our next talk will be September 3rd, 2017 Integrated Nuclear Test in North Korea, results from satellite radar imagery and dislocation modeling by Teng, Wang, and colleagues. And Teng will give the talk. And let's see, are you PC or Mac? You're on the, which one, PC or the Mac?
Mac.
Oh, over there. So we just need to do this here.
Mac. Okay. Okay, thank you, Chairman. And Frank just talked about some very interesting pictures from optical remote sensing. And today I'm going to show results from radar imagery and dislocation modeling. And now all of us have known that on September 3rd, 2 seismic events separated by about 8 minutes were detected in the North Korea's nuclear test set. And the USGS and the China Earthquake Network Center both determined the body wave of magnitude 6.3 for the first event. And from the first impression about this event is that it's much larger than previous test. Even you know nothing about seismology or know nothing about INSAR, we can see from these two figures, this test generates a much large magnitude than all the previous tests. And this is INSAR result shows the affecting area with loss of coherence. And this is a test in 2016 from Dr. Wei. And we can see that for previous nuclear test, it generates a very small deformation area, and it's difficult to get surface displacement measurement. So most of previous tests were studied by seismic data. And this test shows a very large area of surface displacement, allow us to measure it with SAR imagery. And I think most of the audience here is from seismologists, so I basically shows what synthetic upper radar SAR is and how it works. And SAR is a kind of active remote sensing tool. It transmits microwaves to the ground and records the signal reflect back. So for each SAR images, we have amplitude information, represent the reflectivities of the ground, and we have the phase information, record the senses to target distance. And using these two kinds of information, we have two techniques to measure surface displacement. INSAR uses phase differences between two images acquired at different time to measure the surface displacement. This is something like we use a ruler with the length of the radar wavelength to measure very small surface displacement. And the current radar system have a wavelength from 3 centimeters to about 23 centimeters. So we can imagine we use such a short ruler, we can precise measure some very smooth displacement. But when the gradient of the displacement is much larger than the radar wavelength, we got decoration problem. For such cases, we have another method we call pixel offset tracking. We distributed small image patches before and after on the star images, and we calculate cross-correlation surface for each of these small image patches. And from the peak of the cross-correlation surface, we get the shift in two-dimensional. One is in the satellite flying direction, one is in the radar line set direction. And with this technique, we can retrieve surface displacement when even the interferogram is totally decorated. This is a case we applied for the 2010 Wang earthquake. And with pixel offset tracking, we can get large and rapid surface displacement. We can also get north-south component. And if we have satellites flying from different directions, so that we will have measurement from 4 independent directions, so we can easily invert for the 3-dimensional displacement. And we have applications in earthquakes, volcano, and also landslides. Here, I just show you some recent results from measuring the 3-dimensional co-seismic displacement, just to show what modern SAR imagery can do. This is a 2013 Balochistan earthquake. Here, a row shows the horizontal motion, color shows the vertical motion. And this is the 2016 Kumamoto earthquake, and all the circles are GPS data. And this is a 2016 Kekola earthquake. And now we move back to the nuclear test set with these LS2 interferograms. We can see, although it's a large event, but the deformation is localized in this area with about 2 kilometers. And the face is totally decorated. It's difficult to resolve any information from here, but we still can use the low coherence information here. And we calculate the boundary polygon from all these largest cluster of these low coherence pixels. We get an area about 9 kilometers square. It's interesting to see all the tests before, from test 2 to test 5, all located within the same area affected by this test. That means all these 4 tests, all these 5 tests will take place in the same continental, but not the first one. The first one is located outside of this area. And the resolution is very important to get precise surface displacement from offset tracking method. And here I show this is optical image from Google Earth, and this is LS2 SAR images, and we see it's very rough resolution. And luckily, thanks to our colleagues in Germany, in Jeffry, they provide us the Tersa X SAR images. We can see it's much more clear, and we see all the details and in this sub-meter resolution SAR images. And we can easily compare the SAR images before and after the explosion. We can see some changes, even by our eyes. That means there is large surface displacement occurred there. And we have 4 tracks of data, 2 descending, 2 ascending, and 2 of them covering the whole area, and 2 of them covering only south part of this area. With these 4 tracks of Tersa X data, we will get 8 independent measurements, surface displacement measurements. The first row shows the Adams offset result. Is basically a south-north component of the displacement. And the second row is a line offset displacement. It's west-east plus vertical component. It's maybe very complicated to people not in the SAR field, but from these 8 independent data set, we can invert for the 3-dimensional displacement. It shows like this. And so from this map, it clearly shows a divergent pattern of the horizontal motion. And we can also, with this 3-dimensional displacement map, we can also draw 2 profiles and project our surface displacement along these 2 profiles with a vertical displacement. And from this 3-dimensional surface displacement map, 2 interesting features can be recognized. One is the topographic effect. This is not unexpected. Since if we have an explosive source buried at shallow depths, we would expect a surface displacement, something like this. And if we buried in the body of a mountain, we could see something like this. And it's exactly what we saw here. If we do an interpretation for our vertical displacement and show these horizontal motions, we see this south part is a steep terrain here, and also the west part, we show a large horizontal motions. And another thing is the Laeslo uplifting. And from this figure, if we have an isotropic explosive source here, we would generate the surface displacement pattern like this with as large as vertical displacement like horizontal ones. But from our data, we show it's subsidence is dominating the vertical displacement. We only have very small uplifting on the east part of the mountain. And we are trying to figure out why we see these kind of patterns. And we applied the compound dislocation model to the observed surface displacement. It's kind of orthogonal triangular dislocations, rectangular dislocations. And we also account for the topographic effect through simulation of the Earth's surface as a traction-free mesh of triangular dislocations by using this displacement discontinuity method. And with these two kinds of modeling tech, we first try some forward modeling to see if we can reproduce the surface displacement patterns we observed. And the first thing, we ran two models with the same physical parameters, but located at different places with real topography. And we can see it successfully reproduced this kind of topographic effect for the horizontal motions. And we apply this to our data, and it shows very similar pattern for the azimuth offset. And as far as we know that all azimuth offset basically mirror the north-south component of surface displacement is purely horizontal. But it cannot reproduce the range offset, which is read along set in the read along set directions. And see, our models consistently simulate uplifting on the surface. It's only uplifting, but what we observed in the range offset is kind of divergent pattern. This means the horizontal motion is dominant, not the vertical motion. And if we reduce the vertical displacement to about 15 times, and we can successfully reproduce also the range offset. This is very interesting as what we figure out is that after the explosion, what happens to get such reduced vertical displacement? And what we finally setting on model is this. We first extended the inferred point CDM to a finite ellipsoidal source, and so we can also simulate the collapse on the top of the cavity. And then we implement a zone of compaction as large ellipsoidal source, covering the first source. So why we do this is we propose that after the explosion or the uplifting, the crust was fell back due to the gravity. This is different from the volcano source, something like a Mongi source. When the source is expansion, we generate uplifting. But here it's explosion. After the explosion, nothing to support or uplift the crust, and it will fall back, driven by the gravity. And this is our final model setting, and our best result are achieved in a large cavity of isotropic compaction. And with this modeling, we locate the 3D location of the source. It's just exactly on the top of the mountain Mantap, and it's about 450 meters below the top of the mountain. And this is a fitting of our data, and we can see it can successfully reproduce both the azimuth offset and the range offsets. And from this result, we can see during the underground explosions, we first have an explosion, and we generate surface displacement like this. And then we have some localized collapse, maybe on the top of this cavity, and reduce part of this uplifting. And we also have this compaction in a larger area, and so in future reduce the vertical uplifting. And this is what we observed in the geodetic data. It's a combination of these three procedures. So our results suggest that the body of mountain Mantap may be cirrus crust fractured after this sequence of uplifting and subsidence processes. And this should increase possibility of radioactive leakage. And our result also demonstrates that the capability of monitoring underground nuclear tests using radar images. And this is not the complete story. Maybe some of you noticed that we put a small star here, south of the main event. That's the second event we located. And if you want to know more details from the seismology perspective view, please come tomorrow morning to Dr. Sheng Yiwei's talk. He will show perspective from seismology analysis, and will give you a complete story about this event. Thank you.
Time for a quick question.
How big is your source? How much will change?
I don't exactly remember the numbers, but we will have a paper published soon. So with all these details of model details, because the modeling part is was did by my colleagues in Jeffry.
Thank you very much. Okay, the next talk will be intercorrelation of P and PN recordings for the North Korean nuclear tests by Thorne, Lei, and colleagues, and the talk will be given by Thorne.
Okay, I'm going to give some seismological analysis of this, focusing on teleseismic wave analysis. And I think the next talk or later on you'll be hearing about regional moment tensor analysis. So we'll hear quantification of the seismic waves. I think it's very difficult to estimate the size of the explosion from the surface manifestations as just described, and to do it precisely. There's a lot of non-uniqueness in that. But there's also a lot of non-uniqueness in doing it with seismic waves. So we'll do what we can. In this situation, this is looking at the mountain from the south, and these are approximate locations of the sources. These all clustered within the main part of the Mount Maitap, and over here is 2006. Now, I'm going to talk about the relative sizes of these events and their absolute sizes. We're much more precisely able to determine relative size because it can be a differential measurement, though even that has difficulties because you need to know aspects of how the source function is scaling, which depends on their sizes. But then we can also try to calibrate this region for their absolute sizes. And the tunnel entrance going into the mountain, if they're correctly locating the event under the peak, you'd be about 800 meters depth. For it to be up at 400, you would have had to drill uphill. And it's possible, of course, but it's a curious emplacement practice. Usually you want to have a small tilt here so the water drains out, and they see water draining out of the adit, but going uphill would be difficult. And we do believe these are relative locations, as indicated by Frank, that most of the precise relative locations reasonably place the largest event, this blue dot in September 3rd, 2017, pretty much under the peak. 750s to 800 meter topography is quite reasonable. But you can also tell that there is a slope, and that so the burial depth varies between these events. And that's important for the pressure that will be surrounding the source and will influence the degree to which seismic waves couple into the far field. Now, what we would normally do is record teleseismic magnitudes from an event. This is a JVE recording, actually, that was done. And it's recording a small explosion far away. So you're hearing the sound through the rock transmitted, and we can correct for the propagation distance, the geometric spreading, and estimate from log of amplitude a standard magnitude. You can measure the magnitude of this little P-wave pulse. And this is all done with short period P-wave instruments. This is WWSN instrument. That was typical of what has been used in the past. And if you have a site for which you have calibrated the measured magnitude versus yield from knowing some explosions, measuring their magnitudes, you have a new event with some magnitude. You can take its magnitude and predict what its yield is. That typically has been accompanied by about a factor of 2 uncertainty, because there's uncertainty in the slope, there's uncertainty in the intercept, there's uncertainty in the precise coupling event by event. But it is the standard procedure. But that requires that you know what the magnitude yield relationship is for a given test site. Now, we've determined magnitude yield relationships with absolute calibration for Nevada test site, for semi-polytints, and they're very different. And the reason that they're different, and they'll give a magnitude of a comparable yield event that will differ by 0.2 to 0.3 magnitude units, is because there's different attenuation under the Nevada test site, under the Soviet test sites, for example. And you have to calibrate that baseline behavior. All of the waves going down through the Earth have transited through that medium, and unless you correct for it accurately, you could have a bias in your estimate. The slope of these yield scaling relationships also depends on that attenuation, because there's a systematic effect on the frequency content, which influences the magnitude determination. Do we know what the right magnitude yield relationship is for the Nevada or for the North Korean test site? The answer is no. There has not been an absolute yield calibration of it. So we're kind of stuck. If you take the Nevada value and you determine the magnitude, the NEIC, the openly determined magnitude, 6.3, and you plug it in, you get 820 kilotons. If you plug it into the Semipalatinsk or the Soviet test site in a stable platform, you get 293 KT. So there's a huge range in estimated yield, but we don't know which of either of these relationships or whether they're appropriate at all to use. So we have to undertake a calibration of the event directly for North Korea. And unless they allow us to come in and put in Cortex and test how rapidly that burns next to one of their shots, which seems unlikely, we're going to be stuck by bootstrapping our way up from an empirical determination of that. So that's what I'm going to do. Well, I'm going to do two things. First, I'm going to use a method that was developed in the 1980s in the bad old days when there were lots of megaton nukes going off, that we could precisely correct for differences in burial depth and differences in the explosion source function scaling by equalizing waveforms. And the way that worked, and the procedure is called intercorrelation, was take two recordings at a given station. This was from Milrow and Longshot, very adjacent events in Chitka, and the waveforms looked different because there are different events. It's around 80 KT and it's around a megaton. But we had estimates of their depths and we had source function determined from near field scaling that we could actually determine what the shape of the source function was for Milrow and what the shape of the source function was for Longshot, and convolve the Longshot recording with the source for Milrow to make a waveform, convolve the Milrow recording with the source function for Longshot to make a waveform, and these would be identical if we were putting in the correct source functions, their yields, their burial depths to give the PP surface interaction and to account for any spall if that was necessary. That type of waveform equalization can be done with a parameterized model if you have data. Well, there's lots of data for these events. Even for the 2006, there's a good 30 or so decent short period teleseismic recordings with stable waveforms above 1 hertz. For the larger events, there's lots of data. This earthquakes are recorded on hundreds of stations globally that we utilize, and broadband stations filtered to above 1 hertz, 1.2 seconds. And these are just pairs of waveforms for, was it 2009 and the September 2016 event. So you see there's lots of data. And basically these waveforms look very similar because they have identical propagation, attenuation, receiver function effects on each path. So what we are going to look at is how to equalize them even further by convolving each with an approximation of the source function for the other event and optimizing that based on the selection of yields and burial depths for the events. And that's an equalization procedure that will account for the key factors that influence the waveform evolution. Now, it's not using magnitudes, but magnitudes are kind of a silly way to try to measure things because they include implicitly the effects of the frequency-dependent scaling from T-star and from the source function, but don't have any parameterization for it. So we can do better than MB versus yield. Well, you need a parameterization of the source function in order to proceed. We're going to adopt the Mueller-Murphy representation because it's pretty well characterized from observations in different media. We believe that this media is probably granite, it's hard rock near the likely tunnel emplacement sites, so it's a reasonable thing. And if you consider how the source function would look for 1 KT up to 150 KT, the duration will increase as the explosion size increases. As you increase the burial depth, you'll change the pressure function on that explosion source function, so that it's very predictable. So all you need to know is, or specify, is a yield and a burial depth, and you can predict what the source function will look like as long as the little pp reflection off the free surface is elastic. Okay, and that's going to be a problem for the biggest event, but it will hold pretty well, I think, for the smaller events. So we have data, we have source functions, we can equalize the waveforms. This is an example of a pair of waveforms from 2009 and January 16. Station Australia, station nearby. This is a P-wave teleseismic. This is a regional PN observation about 350 kilometers away. See, the waveforms are similar but not identical. They cross-convolve with the source for the other event in the pair, and you should equalize the waveforms. And you can measure the equalized waveforms as a function of assumed yields, assumed burial depths, and do a parameter search. So you have to search over a range of parameters to try and characterize both events to measure a very precise relative yield. Now, you're doing it with absolute numbers, but you have to step through a wide variety of absolute levels. I assume here one event, just for display, we'll assume a yield, we'll assume a burial depth, and determine the properties for, if this were correct, we would estimate that the 2009 event in this case, this is 2006 event, would have a yield of around 1 KT and a burial depth around 400 meters relative to this. So we can determine the differential differential yields and the differential depths more precisely than their absolute values, but we can at least determine them. And that then corrects the scaling of the ground motions for those effects if the Mueller-Murphy source model is right and if the Earth is acting elastically. You can do this for different assumed reference yields, either different yields for the 2016 at 10 KT and 15 KT, and you will get different absolute estimates for 2006 that shift in proportion, but you maintain a constant ratio so that the relative ratio will be more accurately determined by intercorrelation than the absolute values. Okay. Well, you can do that, take any one event and do all of the differential events. What you'll see is that they tend to make kind of these shapes in trade-off space between fairly well-determined yields in each case, fairly narrow in the curvature of these error surfaces. This is modeling the misfit of the total waveform, the amplitude misfit. And wherever you find the minimum in these curves is the best choice. You see a big trough here that is elongated along for a fixed yield estimate over many depths. So the depth resolution is less precise than the estimation of the relative yields. And that's because the differential interference of the little pp waveform is just not as well isolated. But you have the same problem if you do it in the spectral domain. You can do it in the kind of model the modulation of the amplitude spectra. You have the same ambiguity. From that procedure, these relative yield estimates are obtained. Now, I'm just picking a reference for one event, and you're not going to read all these numbers, but I can assume a particular yield for the 2016B, a particular burial depth, and then I can determine self-consistent relative yields, relative burial depths for all the other events. Now, this procedure, then I could take what I estimated for this event and use that as a reference and back evaluate and see how consistent. Do I get the same result that I going either way between these pairs? And you can imagine it's a large parameter space. You can step through many different yields, and it kind of maps out a manifold of trade-off space that's difficult. The consistency is indicated here, though, that if I normalize all these, just divide by the values that I've assumed for this particular event, so that now is 1, I get relative yields that are given pretty consistent results independent of the choice of reference events. So you get precision down to more like 20% fluctuation or scatter, or even smaller in some cases, which is much better than factor 2 for relative yield estimation. One problem, though, the big event probably does have a significant effect on little pp, so it may not be elastic. It's going to have a large damage zone. The waves are going to go up and reflect and come back down through that. The size of the cavity, the dimensions of the elastic zone will influence the result. And we found that if we allow for delaying, it's been observed for many of the larger nukes in the past that the PP arrival was delayed relative to the elastic term. If we allow for a delay of various amounts, we change the estimate for the preferred yield for the 2017 event. So it is dependent, unfortunately, because of its size, on the assumption of how delayed that is. And we converge at fairly large values. That's still a relative yield estimate. That's to an arbitrary choice for the 2016 event. What we've done in addition, you'll find in a poster that's going to be available tomorrow, is that we can do absolute estimation by modeling directly the P waves for the 2017 event because they are so big. They can be seen on broadband seismic recordings. We had about 400 stations with good modelable waveforms. In that case, you have to absolutely put in your T-star operator, you put in a propagation operator or geometric spreading, and you match the average structure. There's strong trade-offs between the T-star you choose and the yield that you'll get, but as a function of how well you fit the waveforms, these are fitting the amplitudes, these are fitting the wave shapes, we can narrow in, and where these curves are both blue and they intersect, on a range of T-star about 0.75 plus or minus 0.05, with yields of around 220 plus or minus 80 KT. With that number in mind, we can then take our intercorrelation relative to that, determine the absolute yields and their uncertainties for all events with their relative depths. So I think this is the kind of bootstrapping approach to calibrating the site through absolute modeling, determining reliable relative yields from that calibration point. A final test that I'll show is that you can take the resulting yields and burial depths pairs and do spectral ratios. This is taking the 2017 event relative to 2006, 2009, 2013. Over on the right, if these curves overlie, your spectral ratios are well predicted, and that supports the resulting estimates of yield and burial depth. And I think for the most part they do. The only one that's not quite good is 2009, where we seem to overestimate the yield a little bit by this procedure, but the other events over a factor of going from 1 KT up to 220 KT are doing very well. So as an absolute calibration, I think it holds up quite well. Thank you very much.
We have time for one question.
I was wondering how your estimated burial depths compare with those inferred from the relative horizontal locations of the events.
Well, they're indicated there on the right. He asked whether the burial depths inferred from the seismic analysis are consistent with those inferred from where they locate the event versus the ADA entrance. So if you look at them, the 2017, 2016 events should all be somewhere around 700 to 800 meters deep. It'll depend a little bit on the volume of the elastic radius. We're getting estimates from 610 to 750. The 2013 event is shallower. 2013 and 2009 are shallower by 50 to 100 meters. 2006 290 in this case. So these are estimates relative to the biggest event. The intercorrelation estimates from just the lower 5 are more stable for depth because you have better resolution of the differential depth. This is assuming the anelastic or non-elastic PP.
Thank you, Thorne. Okay, our next talk is going to be moment tensor analysis of the 3 September 2017 Dprk announced nuclear explosion and collapse aftershock by Jean Ichinose and colleagues, and the talk will be given by Jean Ichinose.
I'd like to start off by acknowledging my co-authors, Sean Ford, Andrea Chang, Bill Walter, Steve Myers, and Doug Dreger. North Korea has conducted 6 announced nuclear tests at the Punggye nuclear test site, shown in this timeline here. Based on the high precision relative locations by Steve Myers, and he has a poster in tomorrow's session for more information. 5 of these 6 events locate beneath Mount Mantap, and we're going to focus mainly on these 5 events. The recent event locates beneath the peak here. And so the take-home of this talk is, based on moment tensor analysis, the recent event is identified as an explosion-type mechanism, and it was followed 8.5 minutes later by an aftershock, and we've identified that as a collapse mechanism. So the outline of our talk is, first we'll give the moment tensor inversion results of an example earthquake near the test site. We'll show the results of the explosion, the collapse, and the source types, their network sensitivity solutions. We'll compare the volume for the collapse compared with the cavity volume of the explosion, and then we'll wrap up on some previous work that we did on differential surface wave analysis. So this is an example of a MW4 earthquake, a normal faulting event about 75 kilometers southwest of the Punggye test site, occurred in 2002. Here's the DV toric moment tensor solution. The stations I used here are in red. The data is in black, red is in synthetics. Blue are data that we did not use but we predicted. Here's the full moment tensor solution here, and we get an isotropic of about 26%. But if you're trying to discriminate explosions with earthquakes, this is actually a negative isotropic, so it's actually farther away. So here's the example of the recent explosion using the same 3 stations in China, shown here in red. The MW is 5.4. The isotropic is 63%, and we have a very good variance reduction of 97%. Here's the moment tensor inversion results for the collapse. It's an MW 4.5, 69% isotropic, and the variance reduction is much lower at 70%, and that's because this is in the coda of the previous event. So to show where these plot in source type space, we've adopted the tape and tape method of showing eigenvalues on a sphere. He has these 2 angles. One that you could think of as a longitude that represents a CLVD, and another one that is a colatitude that represents the isotropic, because it's kind of like a Hudson plot. And if we look at the fundamental loon, which is essentially 1/6 of the sphere, we see that the explosion event plots here within the cluster of other nuclear tests. Here along the equator are a sample of earthquakes. And then on the south pole here, which is the negative isotropic axes, we see the collapse event plotting here with the other mine collapse events. The network sensitivity solution is a method developed by Ford and others and has been improved upon by Nanyang and Dreger. Essentially, you take a source type space, in this case the fundamental loon, and you divide it up into a grid of points, and each point represents an isotropic, a CLVD component, and a range of double coupled components. And so you do a forward calculation and compute their variance reduction, and within that range, you contour the maximum variance reduction across the source type space. And this is really useful looking at trade-offs. So for example, with the explosion event, we have the optimal solution here for the explosion, kind of close to a isotropic and an opening crack. But then with the contour of the maximum variance reduction, we see that a negative CLVD fits the data equally well. And similar with the collapse here between implosion and closing crack, and then a trade-off with the positive CLVD. And Doug Dreger has a poster tomorrow where he shows that this trade-off can be reduced using additional constraints like first motions. And for comparison here, I've overlaid the other Dprk tests, and here is a sample of earthquakes in the region from South Korea, North Korea, and northeastern China. So in the source type space for the collapse, we see that it plots more closer to a closing crack than a isotropic. So pure implosion. So we use the crack model for isotropic sources by Mueller as opposed to the spherical cavity equation in Hawking-Richards. And we assume a factor of 2 uncertainty in the moment for the collapse. For the explosion volume, we use the Denny-Johnson relationship in granite. And for the uncertainty range, we assume an MB of 6.1 and then calculate a range of yields based on the mag-yield relationships for a low attenuation test site and a high attenuation test site. So we see that the volumes estimated for the lower yield range overlaps with the crack volume that we estimate from the seismic moment. So it's completely plausible that the collapse event could be explained by a collapse of the explosion cavity. However, without any more information, we cannot completely rule out a scenario like a tunnel collapse. So changing gears, we're going to give you an update on some work that we did previously last year. We looked at the differential surface wave amplitudes and phases. We obtained a good azimuthal distribution of stations by including the broadband array, the FNet array across Japan, operated by NEED. And then for the amplitude ratios, we use peak-to-peak amplitude measured in a narrow band filtered window, shown here as an example. And we're going to focus mainly on 20-second period Rayleigh waves. So these are amplitude ratios as a function of azimuth. For this 6 here are 6 event pairs up to 2016 September. And one thing we notice is that if the 2 events have similar radiation patterns, their ratio is going to be a circle, much like the 2 2016 events. However, we do notice that with ratios formed with 2013 or with 2009, that there is some anomalous radiation pattern with those 2 events. So these 2 occur underneath the mountain slope, and these 2 events, 2009 and 2013, I'm sorry, these 2 events occur under the mountain peak, and these 2 events occur under the mountain slope. We also notice that if we simply take the moment tensors from the regional moment tensor inversions and use those to generate radiation patterns and take ratios of those, they fit the observations really well. And then with the recent event, we have 4 new ratios, and we see similar things like the 2013 event is still most anomalous, and the moment tensor solutions do also fit the data observations really well. Now look at the phase differences. We simply use cross correlation to compute lag times, and we measure lag times as large as a couple of tenths of a second, even though between events the waveforms have very high correlation. We take those lag times and we do a grid search for the relative locations, and we compare those with the body wave locations shown here. Steve Myers fixes the 2016 January event to modeling results of geodetic modeling results using INSAR data. And so when we compare the differences in locations for the 2017 event, the difference is only a couple hundred, less than 100 meters. Same thing with the September 2016 event. And then, however, with the 2013 and 2009, their events are different by over 1 kilometer. So we think there's some sort of apparent source phase shift generated in the source region, and that's not surprising. There's been papers in the literature dating several decades ago that show events in semi-Palatinsk have almost a reversal of Rayleigh waves. So if we just take a difference in the differential travel times with respect to the body wave locations, we get sort of an apparent source phase shift shown in gray here for the 2009 event, 2013, and 2016 September. And since the moment tensor solutions fit the amplitude ratios really well, we thought, well, would they also fit explain the phase shifts? And here shown in the solid lines, they do not, which isn't surprising since the moment tensor solution has a deviatory component, is not unique. So you could probably fit the amplitudes, but there's only one solution that will fit both amplitude and phase. So we came up with a simple moment tensor of isotropic plus vertical CLVD and rotate the CLVD around. And we find that 55 to 75% isotropic, and then a CLVD that plunges 70 to 80 degrees from horizontal in a southeast direction. So that is a CLVD that is pointing, it's rotated into the mountain slope. So to conclude, based on the moment tensor analysis, the recent event is an explosion, and it's followed by an aftershock that has a collapse mechanism. The crack volume estimated for the collapse is within the range of the expected cavity volume of the explosion. So that suggests the second event could be a cavity collapse rather than a tunnel collapse. The relative surface wave amplitude ratios are similar to those formed underneath for events occurred underneath the peak, and they are unlike the ratios formed using the events underneath the mountain slope. And finally, the relative locations of recent event using surface waves places the event beneath the mountain peak, and they are consistent with the body wave location.
So we have time for one question. Any questions for Gene? Thank you, Gene. Okay, our next talk will be a three-dimensional nonlinear calculation of the 2017 North Korean nuclear test by Jeff Stevens and Michael O'Brien, and the talk will be given by Jeff Stevens. 1 second to set you. Are you a Mac or PC?
PC.
Oh, okay. Let's switch keys. Do you see it there?
Yes, 3 up above that. All right, so this talk is on three-dimensional nonlinear calculations we did of the 2017 North Korean nuclear tests. I'm actually going to talk about several calculations. We previously performed 4 three-dimensional nonlinear calculations of a 12.5 kiloton explosion at several depths in the topography of the North Korean test site. Now we have done 2 additional calculations, one of the September 2016 event and one of the September 2017 event, using estimated yields of 20 and 180 kilotons and a location beneath the peak of Mount Mantan. Some results: we find calculated displacements from the 2010 or 17 event as large as 4 meters. We find that the mountain has significant effects on surface waves, and that both the calculations and the data show a reduction in the little pp phase for the 2017 event relative to the earlier smaller explosions. So I'm going to start by looking at the surface waves. These are the measured surface wave amplitudes for the 6 North Korean tests at the 5 closest stations. The picture on the left shows the amplitudes, and on the right, the MS and standard deviation of MS. And as you can see, they're remarkably consistent. There's very little change between stations from one event to the next, and the standard deviations are very small. So in order to do a calculation, we need a yield estimate. We previously, in this paper that we published several years ago, did a careful analysis of the 2009 event and found a yield of 4.6 kilotons for that. So what we've done here is to simply scale the yield of each of the other events by the relative amplitude of the surface waves. And that gives us a yield of this event for this event of 180 kilotons. What I've also shown here on the right, this is the global MS yield curve, and these are the estimated yields of all of these events. As you can see, there's a big discrepancy between them. The offset here in MS is about 0.8 of a magnitude unit. So it's very large surface waves for the North Korean events compared to other test sites. I talked about this on Monday. We attribute this to three factors. One is they're an optimum depth beneath the mountain for surface wave generation. Second, the test site's in a region of extension. And a big effect is that the global data set used for comparison is biased towards low MS for several reasons. These are the North Korean calculations that we did. The earlier ones, from 100 to 800 meters depth, were done at the location of the 2009 event, which is under this slope. The new calculations are done beneath the peak of Mount Mantap. The 540 meter depth shown here is about where we think the earlier events were, and the new events were about 730 meters here, but these are at the same elevation, so they basically correspond to the same adit level. A couple pictures of the North Korean 2017 calculation. On the upper left is the initial state after a tenth of a second, a nice spherically symmetric pressure wave going out from the source. As of 0.2 of a second, it has interacted with the surface very strongly. It hits that, get a negative reflected phase coming back from the surface. Very strong interaction with the free surface. On the lower left here, we show the final tensile cracks in this calculation. As you can see, they cover most of the mountain. And this is along a south to north profile, by the way. And on the right, lower right, is the final nonlinear deformation, which shows the same thing, very large regions of nonlinear deformation. You can look at this a little more closely, look at some of the ground motion from the calculation. I've marked 4 spots on here along this slope, 1, 2, 3, and 4. And what I've shown over here on the right are the velocity records calculated at those stations. And what you can see is all of them have this nice -g slope here, which is an indication of spall at those stations. Basically, it goes, those sites go up in the air and then they come back down under the acceleration of gravity. There's also a lot of motion in the horizontal direction, which basically means that the material is moving sideways off of this slope. The ground motion here at station number 1 actually looks almost like spall in the x direction, but that's probably an illusion. So these are the final subsurface displacements. This is along a south to north profile and along a west to east north profile, both going through the explosion, and it shows an interesting effect, which is that there's very little displacement on the surface. Also, the ones on the left here are the vertical displacement, and on the right are the horizontal displacement. And what you can see is there is not much vertical displacement and not much horizontal displacement either immediately above the above the source, but a lot of displacement on the slope to the south and west of the explosion. This isn't due to cavity collapse because the cavity is still standing. This is just an effect of the topography. I think it's just that the gravity wants the material to move down this slope, and so that's where the motion takes place. Here's a view looking down on the surface. The arrows in both of these are the horizontal displacement showing amplitude and direction. And the colors here are the magnitude of the vertical displacement and the magnitude of the horizontal displacement. Again, this is from a south to north direction, and you can see on the south side of the slope there are large displacements in both the horizontal and vertical directions, and very little immediately above the explosion. So what we're particularly interested in here is the seismic waves from this event. So to calculate the seismic waves, we use the representation theorem. What that means is we save the stresses and displacements on a monitoring surface around the nonlinear part of the calculation, and then we integrate that using the representation theorem together with the Green's function to calculate waveforms. And we use three types of Green's functions. We use far-field body waves, full waveforms, and fundamental mode surface waves. These are shown here on the right as examples for the 540-meter calculation for those three Green's functions. And it's very useful to have those three different types because they each show different things about the source. This slide shows the surface waves and the body waves from the initial set of North Korean calculations from 100 to 800 meters, all at the same yield. And what you can see is there's a very strong depth effect here for the surface waves, with small amplitudes near for the events that are inside the mountain, a peak at the base of the mountain, and then a decrease again as you go down below the mountain. Now the decrease of depth is due to the increasing pressure. What happens to these, I'll talk about it in the next slide. When we look at the P waves also, the P waves don't show such a strong effect. They basically show a slow decline with depth, again due to the increasing pressure. The X here is for an equivalent flat layered calculation. But there are these interesting points which are places where there's a focusing effect from the slope that actually causes an increase in the size of the little pp phase such that it's larger than the initial direct p phase. Surface waves are strongly affected by topography. It's important to understand where surface waves from explosions come from. It comes from the horizontal displacements on a surface outside the explosion. I'm talking about long period surface waves here at 10 seconds and longer. The vertical motion really doesn't contribute much at all to the surface waves, but anything that affects this horizontal displacement will do so. So what happens when you're inside a mountain is that motion just goes into pushing the sides of the mountain into the air, and so it doesn't generate much of a surface wave, whereas if it's below the ground, it does. Here are calculated surface waves from the 2017 calculation. Because it's right below the peak, there's a lot of symmetry in the problem, and so there's really not much variation. This is 8 different angles, and showing 8 different Rayleigh waves here. If you look at it very closely, you can see a little bit of difference, but they're very similar in all directions. On the right are calculated love waves. It does generate love waves. They're not very big. They're about 5% the size of the Rayleigh waves, but they are there. There's no tectonic release in this, so this is strictly due to the interaction with the mountain. So we went back and looked at the love to Rayleigh amplitude ratios for all of the events. And what you can see here is, as I just pointed out, they're small for this event, for the new events, but they're quite a bit larger for the earlier ones because of the higher asymmetry in these locations. And these are measurements, except for a couple of anomalous locations. The love waves were actually quite small for both of these events. So the little pp phase, or the p waves, show an interesting effect also. This is for the 2016 calculation. You can see there's a enhanced p wave in our little pp phase in certain directions, larger than the direct p, but it doesn't happen for the 2017 event. And the reason for that is that nonlinear interaction with the free surface is so strong that it reduces and delays the reflected p phase, reducing the smaller amplitude. And you can see this in the data. This is MDJ from the 2017-2016 events and a clearly larger little pp phase here. You can see this at Incheon and some other stations also. So to summarize, calculation of the September 2017 explosion shows large amounts of tensile cracking, nonlinear deformation in the mountain above the explosion. We got surface deformations as large as 4 meters. Topography has a big effect on surface waves. The direct P wave is essentially unaffected by topography or the free surface interaction, but the little pp phase is strongly affected by both. Thank you.
Time for a question or two? Questions for Jeff?
I have a question.
Yeah.
Now my question is, can you say what the direction of the love wave nodes are? It looked like there were nodes because the phase was reversing.
Yes.
Yeah.
I haven't looked at that closely. I mean, I think it's a fairly typical love wave radiation pattern at long periods, but yeah.
Okay.
It may not be exactly 4 lobe, but it tends to become that way at long periods. But it's, in this case, since it's due not so much to the source itself, but to the interaction with the sides of the mountain, it could be a little different.
I'd also like to point out that his calculations correlate extremely well with our observation, where we observed the greatest amount of surface disturbances where he predicted, and where we didn't see also where he predicted.
I like that comment.
Thank you. I would like to give this talk on behalf of Laeslo Evers, who could not attend the meeting today. And I would like to discuss today with you our findings on seismoacoustic analysis, and in particular on the Dprk events. Well, as we all know, there have been many events in North Korea, as this figure also shows. They have been becoming stronger in time. I had to adjust the scales of the figure to make sure that the last one fitted. But you do see the self-similarity of the waveforms. So the seismic waveforms look similar, but in the atmosphere, they do couple to the atmosphere, and there they do look different. However, the interesting thing is that you can use the seismic and acoustic data together to learn something about the event, and that's the topic of today's talk. In particular, the depth estimates. That is something that we would like to contribute to using acoustic data, as these are difficult to constrain using teleseismic data alone. I've here sort of a cartoon image of the concept of seismoacoustic coupling. You could imagine that if there's a seismic source near the Earth's surface, that the Earth's surface starts to act like a giant speaker, if you will, and will start to emit sounds into the atmosphere. And the sound will start to propagate in all different directions. And depending on how the atmosphere behaves, sound will be picked up at a distant infrasound station. As you can see here, is indicated by this red arrow. And maybe I can use this pointer. That's right. So, and at the same time, there will be seismic energy propagating, of course, at 2 similar stations. And as we will see later, the microbarometer stations that we use for infrasound detections are also sensitive to seismic waves, so you do see seismic energy arriving first, and then infrasound energy arriving. So there's a kind of similar to what Thorne mentioned about the constraining the test sites. There's also the atmosphere plays a role in the propagation, so you have to adjust, you have to correct for the atmospheric propagation when you're trying to interpret your signals, because you will see that they will be quite changed by the state of the atmosphere. And also the noise conditions, they play a role, so we take this into account. And then the overall idea is to understand the contribution of underground and underwater coupling towards the atmosphere, and if then the atmospheric energy could tell us something about the source conditions. Before going to North Korea, I would like to take a small side excursion to the Macquarie Ridge in 2004. We had a paper out in 2014 on this in GRL, where we discussed the observation of seismic, hydroacoustic and infrasound energy on the infrasound and hydroacoustic components of the International Monitoring System of the CTBTO. So to the right you see a record section of the microbarometer station, and you see the PNS energy arriving first, and later there's infrasonic energy arriving later. So this was unique in its sense that it was the first observation of so-called evanescent wave coupling from the underwater to the atmosphere, and it shows the great potential for seismoacoustic characterization of underwater earthquakes, volcanism, and such events of interest. Another recent study that we worked on, and I'm pleased to say that this was accepted today by JRL, was the analysis of the magnitude 6 earthquakes that occurred in Italy in 2016. So we did analysis on this, similar with an infrasound array station in southern Germany this time, IS-26. And for all these different earthquakes that were large enough, we were able to observe so-called epicentral infrasound, so coming from the epicentral region, but also so-called secondary infrasound that comes from different regions and is coupled to the atmosphere. And depending on how the wind blows, you will be able to detect this infrasound at your distant station. So this shows the capacity of the Earth to transmit seismic energy towards the atmosphere and to be picked up by microbarometer stations. Back to North Korea. As I mentioned, there was also several several events that were picked up on the infrasound stations. Today I will focus on the last event in 2017, but also the events in 2013 and January 2016 that were picked up on infrasound stations in the vicinity at IS-45 in Russia at about 400 kilometers distance, and also in Japan at about 1,200 kilometers distance. These events will be then used to try to say something about the source depth. Something that I won't cover today is that but I would like to mention is that this energy was also picked up in South Korea, but this data is not available to us. It's not part of the IMS station, so we are just here using the IMS data. This shows the array processing results that we have done for the 2013 and 2016 events, and I show here the results for the station in Russia at IS-45. So left is 2013, right is 2016, January 2016, and it shows us as a function of time the spectral content, the bass beam, SNR, and the slowness. So here expressed as back azimuth and apparent velocity. And you see a lot of different points here in gray. There's a lot of different energy coming in from different directions. The detections that are of interest are colored here in red, and those correspond to different arrivals that arrive at the infrasound station. So in 2013, there were 3 of them, as you can see here. They're labeled IW, IWS, and IS, and this corresponds to the mode of propagation through the atmosphere. And you will see later that there was tropospheric energy and stratospheric energy that reached the station in Russia in 2013. In 2016, the case is a little bit different. There's a very weak detection that you can see here. I'd always missed it, but if you look very closely, there could be a potential detection. So then the question, of course, is if these explosions are of somewhat of a similar magnitude, so the 2016 January may have been a little bit smaller, why was the infrasound so much smaller or virtually almost undetected at the station in Russia? I also like to mention that there were higher noise levels in 2016, so this also factors into the detection. So it's typically a little bit harder to detect if the surface winds are a little bit higher. So in 2016 it was 2.4 meters per second, so this makes the job a little bit harder, of course. But still, you would expect a sizable infrasound detection in 2016 as well. The blue dots, by the way, I will come back to in a later slide. In this slide, actually. So this shows the propagation conditions from the Dprk test site towards the station in Russia at 400 kilometers distance. It's indicated here by this black triangle. And you can see that infrasound energy is channeled into different waveguides in the atmosphere, the tropospheric waveguide and the stratospheric waveguide. And this depends on how the wind and the temperature is distributed in the upper atmosphere. So typically you get an increase in the around the tropopause. There's the jet stream that points east, and that ducts sound into the troposphere. And then there's a so-called circumpolar vortex, and in the winter it goes east. So in that case, infrasound is also ducted into this waveguide. And you can see here the eigenrays that are indicated by the dashed lines, and those indicate the the paths that the infrasound may have propagated. So if you then figure out or you can predict the inclination angles and the azimuth and the travel time, and those correspond to the blue dots that were shown here, and we could actually show that the observations were bang on with the predictions. It was very nice. In 2016, you see that the state of the atmosphere is a little bit different. You actually get tropospheric and stratospheric rays predicted at the same time. And this has to do with the fact that the stratosphere at this point in the winter has warmed up significantly. There's a so-called sudden stratospheric warming, and that's shown here on this slide. And it showed indeed that in January there's a very hot stratosphere. These are stratospheric temperature conditions at about 45 kilometers altitude. So you get a warm, in this particular point in time, you get a very warm stratosphere, and as a result, the winds are also blowing to a different direction. Normally they flow eastward during the winter, as you can see here in the 2013 case. But due to the sudden stratospheric warming, we had a certain westward jet, and this also inhibited infrasound propagation towards a station in Japan in 2016. We plugged all these numbers together. We also obtained transmissionals from this, which I didn't mention before. But if you combine this data together, the observations in 2016 and 2013, you can then come to some kind of crude estimate of how much deeper the source in 2016 must have been compared to 2013, and we estimated from this a factor of 1.5. And if you then take, for example, a minimum source depth of 450 meters for the 2013 test, assuming a yield of 10 kilotons, this implies that the 2016 test would have been 225 meters deeper. So these are preliminary values. We're trying to get a little bit further on this with coupled seismoacoustic modeling. This is work where Gil Averboeg is working on. He's having a poster on Friday morning, and I invite you to take a look at it. So he is using a wave number integration method to couple energy from the solid Earth into the atmosphere, and he's able to, by plugging into these numbers, able to explain our observations to a first order. The last thing I would like to show is the recent observations in September 2017. So there was also infrasound recorded at the station in IS-45. I showed it here on the right-hand side. As a function of time, you see again the different parameters that I've introduced before. And now I also show the seismic energy that we also observed at the station. So indeed, the microbarometer shaked again, and they picked up the seismic energy. It has a much higher trace velocity, as you can see here. But later, there's a package of energy coming in with more atmospheric trace velocities, so around 350, 340 meters per second. So this would suggest energy coming in from the test site that has propagated through the atmosphere. It's somewhat mysterious yet, as you can see here on the left-hand side, this shows the sound speed profile as a function of height, and I've included all the different ensemble members that we get from ECMWF for the numerical weather prediction, and they show that you would not expect any stratospheric propagation. So this is something that we're working on to be able to understand why we observe the infrasound so well, and it's not yet explained by the atmospheric models. With that, I would like to summarize what I've just talked. So underground tests and earthquakes generate seismoacoustic signals. Clear infrasound has been detected in IS-45 in Russia in 2013 and 2017. In January 2016, we had a weak detection. So we'd like to use these kind of observations to say something about the depth of a source. So we have a preliminary depth estimate that I've mentioned. We're working on this further in our seismoacoustic propagation modeling, and we're also further working on trying to understand the uncertainties in atmospheric propagation modeling by looking at different ensemble members, the uncertainties that are in the atmospheric models. And but my message for you today is the use of seismic and acoustic data together could be useful to constrain source parameters. And with that, I would like to thank you and take your questions.
Any time for questions?
Given what we saw earlier today in the session, is there some chance that the source itself has directivity?
Yeah, that's a good question. You mean in the 2017 case?
Yeah. So there seems to be more motion on one side than on the other.
Yeah, it could be very well be the case. We'll be very interested to take a look at that and see if that factors into the propagation as well. So this all assumes what I just said, and propagation from a point source above the test site, and whether or not this is the case is the question.
Take the other question too.
Presumably the subsurface is changing, through time, fracturing and collapsing. Do you think that affects the coupling, the seismic coupling around?
You mean at the test site?
Yeah.
Yeah, could be interesting to figure out. We'd like to have an accelerometer on top of the mountain. Then.
Any other quick questions? Well, Danny?
I'm curious that your ECMWF did not predict a stratospheric return in 2017. Can you comment on the relative possibilities of, an error in the upper atmosphere specifications versus gravity wave energy, which has been known to scatter signals into shadow zones?
Yeah, that's an interesting point. We've looked at different ensemble members, not only this is what I showed, this is the so-called EDA, the Ensemble of Data Analysis. There's also the forecast models that ECMWF produces, and in fact it shows large variability. Whether or not gravity waves play a role is another question, of course, that you could think about. We do see very clear arrivals, so that would not be indicative of small-scale structure, but rather well-developed refraction.
So it does sound like it's an error in atmospheric specification as opposed to a small-scale perturbations of gravity wave energy?
It is a possible scenario, but we should rule out all different things. So it could also be, for example, a source condition. So this is work in progress.
Thank you. Oh, okay.
Talk about the synergy between seismics and infrasonics. What the fact is, when you came up with that 1.5 different, 1.5 times different depth, we also see that empirically with all the locations, the INSAR data for the 2016 January event occurred vis-a-vis the 2013 further down slope. So you have that to work with as well. In other words, there's another data set that should be synergized as well.
Yeah, absolutely. Yeah, I'm pleased to see that the results are consistent. So yeah, that's nice. Yeah.
Thank you, Jan.
Thank you.
Okay, the last talk in the session is IMS radionuclide monitoring after the announced nuclear test of the Dprk on 3 September 2017 by Jolanta, Kusmierczyk-Michulec. I apologize for mispronouncing your name, and colleagues at the CTBTO. Are you on the PC?
Yes, it is downloaded. It's uploaded.
Okay. Yeah. It's just,
It's here. Hmm? And this laser?
oh, it's right here.
Ah, okay. And,
But there.
okay. Good afternoon. My name is Jolanta Kusmierczyk-Michulec, and I would like to give you some details related to IMS radionuclide monitoring after the announced nuclear test of the Dprk on 3rd September 2017. My co-authors are listed on the bottom. So during my presentation, I will give a few details related to IMS radionuclide detection system, and also I will present briefly atmospheric transport modeling that we are using at CTBTO. And also I will give some examples of operational application of the tools that we are using in the process of monitoring in cases like Dprk. First of all, I would like to emphasize that the moment CTBTO's monitoring station pick up an unusual seismic event in Dprk, on top of routine operational radionuclide monitoring, special efforts were undertaken to make sure that any possible signal from a release following this event would be captured, analyzed, and that state signatories will be informed in a timely manner. The international monitoring system developed by CTBTO is a global system of monitoring station, and it's important to emphasize that we have 4 different technologies: seismic, hydroacoustic, infrasound, and radionuclide. And this is the map showing all stations. During today's talk, I will focus on the radionuclide station. So just for your convenience, I highlighted the location of radionuclide station. In total, radionuclide network includes 80 stations, out of which 40 are to be equipped with a noble gas system. And the aim of radionuclide station is a global monitoring of radioactive aerosols and radioactive noble gases, supported by atmospheric transport modeling. So those two graphs shows status of the CTBTO network near Dprk. So it's just the extraction of, it's a kind of sub network showing the location of the station that that are located around Dprk. For the left panel shows particulate station. In total, 9 stations were operating in 2017. And in case of noble gas station, we had 5 stations operating. So those belong to the closest network near Dprk, but I need to also mention that obviously we take into account all other possible detection at all stations. Whether a certain detection can be detected, whether a station can detect something, it also depends on the atmospheric conditions. So, for example, this plot here shows the monthly sensitivity. So it means it shows how many times during a month a given a hypothetical release of a xenon 133 from Dprk site would be detected by a station. And the fact that you can see some kind of seasonality effect, some kind of cycle, it's related to the atmospheric conditions, so the wind pattern. It demonstrates that, for example, during the summer, during the winter time, like January, February, the number of days during a month is very low. This kind of seasonal effect for the Takasaki station is less visible, but still there are some differences depending on the month. In case of this station, Chinese station, the wind direction is such that the number it's very rare that the wind is blowing in such a way that anything released from the Dprk site would be detected by the station. This plot illustrates the timeline from release to radionuclide detection. So if there is an event, it needs to the moment until the station will detect something, it takes some time. So it's related to atmospheric transport. So it can take, depending on the where the station is located, it can take between 1 day to 2 weeks, and sometimes even longer if the station is located farther, or if simply the air masses make some kind of strange trajectories. Also, when the air masses will arrive at the station, depending on the network, depending on whether it's a particulate station or noble gas station, time related to processing of data, it takes between 3 days for particulate system to 2 days to noble gas system. This is just to give you an idea that the event that happens that can be detected by a radionuclide system, but it takes some time. At CTBTO, we are doing on a operational. We are doing operationally global model, so global scale. We are running a FlexPart model. It's a Lagrangian particle dispersion model. So it's a global model with low resolution. Low resolution, it means we are using at the moment 1 degree spatial resolution, but we are moving to 0.5 degree. For operational purpose, we are using 2 types of meteorological data, ECM-WF data and NSEP. And at the same time, we are working on developing the high-resolution model, and this is an example of the plume. This is an example of a test that we did for this event. So operationally, we run ATM model in a backward mode. So it means that from the receptor location, and the purpose is to use atmospheric transport modeling to identify the origin of the associated air masses. And in special cases, we do as well forward modeling. So it means from the location of the waveform event, and the purpose is to predict which of IMS radionuclide stations are likely to be affected by potential radioactive release. This is an example of the forward simulation that was generated using NSEP forecasted data, and it shows transport of air masses during the 7 days, and the release time is corresponds to the main event. And thanks to this type of simulations, we can see which IMS stations will be can observe something. So it's really very helpful to have this kind of simulation. Also, we do forward simulation for events like aftershocks. So each aftershock event was, for this kind of event, we did also forward simulations just to check which of IMS station will be affected, and to try to estimate the activity concentration that can be measured at the station. We also are assuming different, considering different scenarios like prompt release, continuous release. And this graph shows example of the predicted activity concentration and gives idea where the plume and when the plume can arrive. So the air mass trajectories provides a link between radionuclide release and detection, and in the process of verification, it's very important to know about civil sources like nuclear power plants or isotope production facilities, because they can contribute to the background signal, and it will and knowledge of them helps to interpret the results. So this is an example of background of xenon background for a Japanese station in Takasaki. And the red dots represent level C data, so it means it's abnormal detection. And as this graph demonstrates, this kind of abnormal detection is observed at this station quite often. So that's why the history and also knowledge of other civil sources is very important. This, what I was presenting till now, it was about forward modeling, but we also do backward modeling. So the backward simulations have the purpose to identify the possible source of detection. So if any IMS station detects an elevated level of radionuclide, the ATM in a backward mode is used to identify the origin. In case of one or two detection, we are using so-called field of regard concept. So this graph demonstrates this. So this is based on two detection that we observed during this in this phase of monitoring. One detection was at the station in Hawaii on the 7th of October. It was level C, and the other detection was on 2nd of October at Japanese station. So if we just overlap air masses related to this event and look at the backward trajectories, we see that they come over Dprk, but also the possible sources can be somewhere else. This is better demonstrated on this graph here. So in case of multiple detection, we are using the concept of possible source region. And the idea is that for each grid point in space and time, we calculate the correlation coefficient between the simulated activity concentration, which are calculated based on ATM, and detected and measured activity concentration. And the result of such a study of this kind of concept is presented here. So this is the correlation coefficient. So the scale present correlation coefficient. The red color shows area where there is the highest correlation. So as you may notice, there is a large correlation for Dprk side, but also other regions are indicated. So it means that there are also other potential sources that would explain the detection observed at a Japanese station and this Hawaiian station. So to summarize, no CTBT relevant radionuclides were detected by the IMS station that could be unambiguously linked to a nuclear test in Dprk in September 2017. If we compare events like Dprk in the past, we have to admit that each event is different and requires a specific approach. And 3 months later, so it means now we are in December, the chances to still observe a late release of radioactivity are decreasing. So with this statement, I would like to conclude my presentation. Thank you.
Questions?
You had some very interesting slides about atmospheric transport. Is there anything that you can constrain or theorize about the source function for the introduction of radionuclides into the atmosphere? Is it instantaneous, delayed by days? Does it decay with time? I know that's a tricky area. But is there anything you can say?
Well, this is an interesting question. Because we don't have this knowledge what kind of actual release is, or if it was or not. So it's just the hypothetical release, and then we are considering a different option. I mean, because of our knowledge is limited, so we analyze a different scenario, like a prompt release, continuous release, and we try to see whether our hypothesis match the observation. And also the plume that I was showing, this moving animation, the animation showing this moving plume, it's based on the assumption that we are considering air tracer, and then after that we just in the process of post-processing, depending on what kind of detection was observed, we may just simply do the post-processing and include the fact that that it was, for example, xenon 133 that was detected, so we just use this decay time related to this.
Is the lack of a clear detection possibly indicating that the explosion was deeper than assumed?
I mean, our knowledge is quite limited. So we have the observation from the station, and then we have some other information. But I mean, I'm atmospheric sciences officer, so I mostly work with the atmosphere. So we consider. Our simulation using FlexPart are done for the whole atmosphere, but the output is for the lower level, so between 0 and 150 meters, just to represent the altitude at which our stations are located. So that's.
Okay, I think we'll take the rest of the discussion to the post session. Just 2 quick announcements. First, the session is going to continue tomorrow morning at 8 a.m. in a different room, room 225 and 227. And second, I neglected to mention that there's a special issue of the Seismological Research Letters with a call for papers on this event and its aftermath, with papers due by May 1, but they'll be accepted and starting to review as soon as they're turned in. So with that, I want to thank all the speakers, and we'll come back again tomorrow morning at 8 a.m. Thank you.